Hello, this is Engineering Statistics and Linear Algebra 18 EC44, Module 4, Lecture 11, Part 3. So we are talking about the chapter on orthogonality, and under this, the topic to be discussed today is cosines and projections onto the lines. So we discussed in the last class about orthogonal vectors and orthogonal subspaces. I'm Dr. Nurullah Sharif, Professor and HOD, EC, CCAB Institute of Engineering and Technology, Vijaypura. So we want to find, say, the distance from a point B to a line in the direction of a vector A. So we have here a point B, point B. We have this. From this, we want to find the distance, or rather the nearest distance, least distance from on the line in the direction of the vector A, on the line in the direction of the vector A. So, and the point corresponding to that will be the point P. So we are bothered about finding the point P. So line connecting V to P, this line connecting V to P is definitely perpendicular to, so you can see that this line connecting V to P is perpendicular to the A. So this is the line which connects from B to P, and that is perpendicular to A. Also, this B is nothing but this component plus this component. This is the parallel component to A, and this is the orthogonal complement to component of the what you call B. Okay, parallel component of B in this direction is the P, and the orthogonal component of B is this in the direction of A. Okay. So this fact will allow us to find the projection of P, projection P of P. Similarly, if a plane is given to us in place of a line, or for that matter, any of the subspace, yes, instead of a line, the problem is to find the point P on that subspace that is closest to B. So the one which is closest to B will definitely be, perpendicular or orthogonal. The point P joining B will definitely be orthogonal to the subspace. Yes. So this point P is the projection of P onto the subspace, and this will be perpendicular from the B to the S, or B to the P. P will be in on S. So a perpendicular line from B to S meets the subspace at P. Geometrically, that gives the distance between the points B and the subspace. Yes. So this is exactly the problem of least square solutions to an overdetermined system. What it means is that B might represent, the vector B might represent data from experiments or questionnaires. We might be collecting data using experiments, or we might be collecting data using questionnaires. All this will correspond to B, and it contains too many errors to be found in the subspace. Most of the time, whenever we do the experiments and the questionnaire, there is a possibility that it might contain too many errors in too many errors, and from this we can't just find the exact value for the perpendicular distance. So B itself, we can't find the exact value. When we try to write B as a combination of the basis vectors for S, this cannot be done, because we see that the questionnaires or data, they might give us an inconsistent equation corresponding to the Ax equal to B. And Ax equal to B, once it is inconsistent, it has no solution. So the only way we can solve this is the least square method selects P as the best choice to replace the B. So we need to use the least square method to find the best choice of the value of x. That is the best choice for the value of x, or rather estimate of x, you can say. We are going to estimate the value of x. We can't find the exact solution for this, but we can estimate the value of x. How do we do that? Projection onto a line. We want to find the projection point P, and this point must be some multiple. P is equal to x hat of A. So this x hat of A is the estimate, value of x multiplied by the A. P is nothing but the estimated value of A multiplied by A, and this estimated value of x is just a constant, is a multiple, and this will be on the line. Naturally, P is there on the line, and it's definitely a multiple. So every point on the line definitely is a multiple of the vector itself. So the problem is to compute the coefficient x hat. So this is a constant or coefficient which whose value has to be found, and this estimate has to be found. So we should remember that whatever is the line which joins B to the point P is closest perpendicular to the vector A. B joins P, and P is equal to x hat A, and that is the line joining B to P is perpendicular to the vector A. We know this, and because of that reason, we can try to find that the the orthogonal component which is there will be the B minus XA or B minus P. B minus P will give us the orthogonal component, and that will be orthogonal to A. So if B, what you call the line B to the closest point P will be orthogonal to the vector A, and hence B minus XA will be perpendicular or orthogonal to A. Hence, we are trying to write B minus XA is perpendicular to A, and that gives us might be B minus XA transpose A, or A transpose B minus XA. Either of the two one can write. So we'll consider A transpose B minus X hat of A equal to 0. And if we rearrange this equation, we'll get A transpose B is equal to X hat A transpose A. And definitely X hat will be A transpose T B by A transpose A. So this A transpose B is just the dot product of A and B, and the A transpose A is the dot product of A with A itself. This is dot product of A with B. This is dot product of A with A itself. That gives the formula for the number x hat. Okay, the coefficient or constant estimated value will be this, and the projection P we can try to find from the value or from the formula x hat of A. So P is equal to x hat of A will be naturally equal to this estimated value multiplied by A. Now we can try to find a projection matrix of rank 1. We see that the projection onto a line is carried out by the projection matrix P, and written in this new order. We can see that the if the matrix P is multiplied by the B, the matrix P is multiplied by the B, then we are going to get a point P itself. And that can always be written as P is equal to capital P into B, and we can write back whatever we have written earlier in a reverse format. Here we can bring first, in place of x hat A, we can write AX hat. So this is AX hat, and once having written this, this is same thing as telling that it is AAT by 80A multiplied by B. So that means P will be equal to AAT by 80A, and that is what is written over here. That is what is written over here. So let us consider some examples. The matrix that projects onto the line through A can be found out. The question can be find the matrix that projects onto the line A. Okay, find the matrix that projects onto the line which is A, represented by which is spanned by the A. So that will be R, which goes through A, line through A. So, so the P is AA transpose divided by ATA. AA transpose divided by ATA. So A can be written as, this A can be written as the, what you call column matrix of this, that is this. And A transpose is the row matrix of this, that is this. So having written that, then ATA is the row matrix of this, that means this first, and A will be this next. ATA means first this, then this. And that will give us ATA is equal to 1 into 1 plus 1 into 1 plus 1 into 1 equal to 3. So that means ATA will be equal to 3. And if you multiply this with each other, then you'll get a matrix, which is a complete matrix, 3 by 3 complete matrix with value 1, this quantity. And that divided by 3 will give us, a what you call complete matrix with all the elements equal to 1 by 3. So you can clearly see that the rank of this matrix is definitely equal to 1. Rank of this matrix, because all these are same, they are all dependent rows or dependent columns, right? Dependent rows and dependent columns. So if you take the LOD decomposition, this will just become 1 by 3, 1 by 3, 1 by 3, 0, 0, 0, 0, 0, 0. So this matrix has two properties, and that is typical of the whatever properties are there, that is typical of the projections. So now those properties are P is a symmetric matrix. We can see that P is a symmetric matrix, and its square is what you call, if you take the square of that, then it will get the same thing back. So this is a typical projection which we have already seen. The second example is projecting onto the theta direction in the xy plane. Projecting onto the theta direction in the xy plane. So that means might be the what you call B, the point B is in the theta direction of the xy. Then at that time the line goes through A equal to cos theta comma sin theta, and the matrix is symmetric with P square equal to P. So projection means it is just rotating in the theta direction, and that will be P equal to AA transpose ATA. So rotation will give us this. A is equal to cos theta and sin theta. AAT will be, in place of cos we are using C, in place of sin we are using C. So A can be written as a column matrix corresponding to this, that is CS. A transpose can be written as the row matrix corresponding to this, which is this. And again, A transpose is the row matrix corresponding to this, which is written like this, and A is the column matrix corresponding to this, which is written like this. So we'll get C into C, C square, C into S, CS, S into C, or C, SC or CS, both are same. S into S will be S square. And if you multiply this, it will be C square plus S square. C square plus S square is cos square theta plus sin square theta, that is equal to 1. So thus we will get this value as 1, and hence only what remains in the numerator, which is here. So we need to project this B onto A. For that, we need to multiply the projection matrix, which is there here, B, P, with the value B to get the point P. To get the point P, we should multiply this matrix P with the B. So if say B is given to us, then the projection of B onto A can be found out by just multiplying this, what you call P, with the value of B, multiplying this with the value of B to find the projection of B onto A, which is nothing but P. So let us take another example. Find the distance from point x equal to 3, 1 to the line spanned by y equal to 2, -1. So we will now consider that the, what you call, the point x is broken down into two parts. One is the decomposed into two parts. One is the parallel with y, parallel with this, which we are interested in, and another is perpendicular or orthogonal to this y. Okay, the orthogonal to this y will give us the, what you call, distance to be measured. The orthogonal will give us the distance to be measured, and that is the one which is more important, right? So the required distance is the length of this orthogonal component O. So T will be equal to y dot x, that is, y transpose x divided by y transpose y into y. So y dot x or y transpose x, y dot y or y transpose y into y. So in place of, what you call, in place of the A, we have y, and in place of B, we have x here. So therefore, we can write like this, right? In place of what you call B, we have x, and in place of A, we have y. So therefore, that will become y transpose x divided by y transpose y multiplied by the value y, right? So this is your estimated value. This is your estimated value. So y dot x or y transpose x can be written as 2 and -1 in the matrix format, in the row matrix format, and then 3 and 1 written in the column matrix format. So that will give us 2 into 3, 6, minus 1 into 1. So that will be 6 minus 1 equal to 5. Then the y dot y will be 2 into 2, 4, plus of -1 into -1, that will be +1. 4 plus 1, 5. So 5 by 5, y vector is given here, 2 minus 1, which is the point which basically spans the line. So line itself can be represented by this multiplied by some constant c. So this value 5 by 5 will be 1, so we are just left with this. So we having found P, we know X, we can find O. O will be X minus P. So X minus P is equal to 3, 1 minus 2, minus 1, and that will give you 3 minus 2 is equal to 1. 1 minus of minus 1 is equal to 2. And having found the vector O, which is orthogonal to Y, the distance of that can be found by just taking the distance vector, that will be 1 square plus 2 square root, and that will be root of 5. Next problem is find the point on the line. Find the point on the line y equal to -1, that is closest to the point 3, 4. So we need to find a point on this line, that is P we need to find, that is closest to the point 3 comma 4. So this is your B, right? P we need to find, we are given the line, so we need to find the what you call A, or might be what is known as a vector, which spans this line, which spans this line. So the required point is the projection P of V equal to 3 comma 4. So we are considering 3 comma 4. This is nothing but B. This is like our B now. This is like our B now. And we need to find the what you call vector A. Vector A will be correspondingly, we can write W equal to 1 comma 1, which spans the line y equal to minus 1. How do we get this? The only way is substitute some value of x and get the value of y. For example, x can be substituted as 1, then y will become minus 1. If you substitute x equal to minus 1, no problem. Then y will become plus 1. So you can write that. Or you can put x equal to 2, then y will become minus 2. So that is the only way we can find this value. So effectively spanned value will be, the line this line can be represented by c into 1 of 1 comma minus 1. So w equal to 1 comma minus 1 spans the line y is equal to minus 6. So having done that, we just need to take the, v dot w, v dot w, okay, v dot w or w dot v does not matter at all because both are same. So v dot w or v transpose w or w transpose v, either of the two, okay, that can be written over here, divided by w transpose w or w dot w, which is written here, multiplied by the w. And this is nothing but now this multiplied by this dot product of this. So 3 into 1 minus of plus of 4 into minus 1. 3 into 1 plus of 4 into minus 1, that will give us minus 1. Similarly, this dot product with itself is 1 into 1 plus of minus 1 into minus 1, that will give us the value 2. And the w itself is written over here, and hence we'll get minus half comma plus half. So this finishes the